So next up on our discussion on the topic of magnetic field, we have current carrying conductor. An electric current is comprised of moving charges. Thus, a current carrying conductor may also be considered as a magnet. A current carrying conductor or a wire in which you have a current flowing through the wire. A current carrying conductor is a magnet, just like a moving charge, and just like a moving charge, the current carrying conductor is affected by a magnetic field. That is to say, the magnetic field will apply force on the current carrying conductor. Say that you have a current carrying conductor, you have a wire, current I is flowing through the wire. We place the current carrying conductor inside an external magnetic field B. Since the wire, the current carrying conductor is a magnet, the magnetic field will apply force on the current carrying conductor. The force applied by the magnetic field is given by F is equal to IL cross B. I is the current flowing through the conductor. L is a vector. So vector quantity, same direction as I, as the current I. And the length or the magnitude of vector L is length L. Length of the conductor segment that is inside the magnetic field. F is equal to IL cross B. You have cross product. So again, please review your cross product in your vector analysis. F is equal to IL cross B. You are multiplying L and B together, vector multiplication. And the answer is a vector quantity. Magnitude of the magnetic force F as per vector multiplication, as per cross product. Magnitude of F is given by F is equal to ILB sine phi. Current I, length L, magnitude of the magnetic field B, and phi is the angle between vector L and the magnetic field B. Phi is the angle between L and B. F is equal to ILB sine phi, magnitude of the magnetic force applied by the magnetic field on the current carrying conductor. For the direction of the magnetic force, use your right hand rule, the right hand rule of cross product. As an electromagnet, as a magnet basically, a current carrying conductor will produce its own magnetic field in the surrounding space. This magnetic field is described by the Biot-Savart law. Suppose we have a current carrying conductor or wire. Current I is flowing through the wire. Let's take a look at a very small segment DL. DL is a vector quantity, same direction as the current I. This very small segment will produce a magnetic field, a very small magnetic field at point P. Very small magnetic field, dB. And the Biot-Savart law tells us that dB is equal to mu naught over 4 pi times I dl cross r hat divided by r squared. R hat is a unit vector that is pointing at point P. Unit vector, magnitude of 1, no unit, the only information contained is direction. R hat is simply pointing or giving the direction pointing at point P. From DL towards point P. P is distance R from the segment, from DL. So distance between DL and point P is R. And mu naught is the permeability constant. Mu naught is equal to 1.26 times 10 to the negative 6 Tesla meter per ampere. The Biot-Savart law, dB is equal to mu naught over 4 pi I dl cross r hat divided by r squared. Integrating dB will give you the total magnetic field B at point P. Integrating this side will give you total magnetic field B. Integrating the other side, you're basically integrating dl. We integrate dl in such a way that we form the shape of the current-carrying conductor. And note that we have cross product in the equation. You have dl cross r hat, meaning before you may integrate, you have to evaluate the cross product first. dl cross r hat. For instance, consider a very long, straight, current-carrying conductor. Say you have a conductor, straight and very long. You have a current I flowing through the conductor. Let's take a segment DL located in this direction. DL again is a vector quantity, same direction as the current. And we consider the magnetic field produced by this segment at point P. Point P is distance capital R from the center or middle of the conductor. DL is distance small r from point P. R hat is pointing towards point P. So you have R hat and DL, same direction as the current. The angle between DL and R hat is angle theta. Evaluating the cross product in the Biot-Savart law equation, we have dB is equal to mu naught I over 4 pi dl sine theta divided by r squared. Magnitude of the very small magnetic field dB produced by dl at point P. Now, r is basically the hypotenuse of a triangle with sides capital R and let the other side be length L. Once we integrate dl to form the shape of the conductor, L will be the total length of the conductor. So you have a triangle, hypotenuse small r, side capital R, and side L. R squared is equal to capital R squared plus L squared. Again, small r squared is equal to capital R squared plus L squared. You have a right triangle with hypotenuse small r. Now, sine theta, sine of theta, if you use supplementary angles identity for sine function, you have angle here. This angle is 180 minus theta. If you get the sine function of this angle, this will give you the same answer as sine of theta. So sine theta is equal to sine of 180 minus theta. Sine function is opposite over hypotenuse. So sine of this angle is opposite over hypotenuse. You have capital R divided by hypotenuse small r. hypotenuse small r is just the square root of this equation, which will give you capital R divided by square root of r squared plus L squared. Let's replace sine theta by this equation. You have mu naught I over 4 pi times r dl divided by r squared plus L squared quantity to the 3 halves. You have r squared times square root of r squared plus L squared. That will give you the denominator of the equation. Integrating the equation, integrating dB will give you the total magnetic field at point P. But note that we make the integration easier if we only consider first from this location to the end of the conductor. From 0 to the other end of the conductor. Since the conductor is considered to be very long, let's consider the conductor to be infinitely long. So from 0 to infinite. It's easier to integrate from 0 to infinite than from infinite to infinite. So we integrate dB from 0 to infinite, and then simply multiply the equation by 2 to take into account the other half of the conductor. So we have total magnetic field B at point P is equal to 2 times the integral of dB. We integrate from 0 to infinite. From 0 to infinite, and then we multiply by 2 to take into account the other half of the conductor. Thus, we have B is equal to mu naught I over 2 pi integral from 0 to infinite of r dl divided by r squared plus L squared quantity to the 3 halves. Integrating this equation will give you mu naught I over 2 pi r. The magnetic field B at point P has a magnitude given by mu naught I over 2 pi r, where r is the distance between point P and the center or middle of the very long straight current carrying conductor. Magnitude of the magnetic field. For the direction of the magnetic field, use the right-hand rule of your cross product. Remember that for the bios of our law, you're multiplying cross product dl cross r hat. So dl cross r hat. Use your right-hand rule to determine the direction of the magnetic field at point P. Or you may use the other right-hand rule, a simplified right-hand rule, just for this situation. Get your right hand, get the thumb of your right hand, align the thumb of your right hand with the direction of the current, and the direction in which you may close your fingers at point P, the direction in which you may close your fingers will tell you the direction of the magnetic field at point P. So you have two right-hand rules that you may use. You may use the right-hand rule that I had just mentioned, or you may go back to the basics, use the right-hand rule of cross product, dl cross r hat, use the right-hand rule for that cross product to give you the direction of the magnetic field at point P. Dividing the equation by 2, we get the magnetic field at point P for a semi-infinite wire. For a semi-infinite wire, the magnetic field at point P is simply half of the equation that we had just derived. B is equal to mu naught I over 4 pi r. Again, use the right-hand rule to determine the direction of the magnetic field. This is magnitude of the magnetic field at point P. Use right-hand rule to determine the direction of the magnetic field at point P. Similarly, we can use the Biot-Savart law to determine the magnetic field produced by a curved current-carrying conductor. So previously, we have a straight wire. Now we have a curved wire. Basically, you have an arc, the wire or conductor forming an arc. We convert dl into d phi, and we integrate d phi to form the whole arc, to form the shape of the conductor, and we get the following magnitude of the magnetic field at point P. Distance r, radius of the arc, distance r from the conductor. B is equal to mu naught I phi over 4 pi r, where phi is the angle of the arc angle, and it must be in radians. Again, use right-hand rule to determine the direction of the magnetic field at point P. I can't stress that enough. Please go back to your vector analysis, vector algebra, and please review your cross product, particularly the right-hand rule. Of course, for this situation, just like in the very long straight current-carrying conductor, you can use the right-hand rule that I had mentioned. Align the thumb of your right hand, align it with the direction of the current, and the direction in which you may close your fingers will give you the direction of the magnetic field at point P. Right-hand rule simplified for this situation. You may also use that same right-hand rule for the curved current-carrying conductor. Again, you can also go back to the very basics, apply the right-hand rule of the cross product if you want to. If we set the arc angle phi to 2 pi, which is the angle of a whole circle, the curved conductor will form a circle. We have a circular current-carrying conductor of radius r. The magnetic field at the center of the circle of the circular current-carrying conductor is given by B is equal to mu naught I over 2r. For a more complete picture on force experienced by a current-carrying conductor, you might want to look into the concept of torque on a current loop. And that's it for now. That's it for our discussion on the current-carrying conductor. We'll continue our discussion on magnetic field in the next video. In the next video, we take a look at the concept of parallel conductors. So again, that's it for now. Thank you for watching.